Welcome, everybody. Thanks for joining today. My name's Jennifer Griffith, and I work at the Northeast Waste Management Officials Association, otherwise known as NYMOA. We are an interstate association of the 6 New England states, New York and New Jersey. We were formed by the governors back in the 1980s. And then subsequently, New York and New Jersey joined. So we're an interstate association of the 6 New England states, New York and New Jersey, focused on, or our members are the solid waste programs in those states, the hazardous waste programs in those states, the pollution prevention and toxic use reduction programs, and then also the waste site cleanup programs. And so that's what we're doing here today. The waste site cleanup programs, their priority for work through NYMOA is training. And so we've got a great webinar today on borehole geophysics and an excellent presenter in Mark Domaracki. I told him I would mess that up. So just a couple logistics though. We will be sharing a PDF of Mark's slides after the event. So I will show you where that'll be posted, but I'll also send around an email. We've got quite a few people on the webinar today, so we will be doing questions. You'll have to type them in. So everybody should have a control panel. Go to webinar control panel. Everybody has their own, nobody sees yours. And in their control panel, there should be a questions section, and you can just sort of open that up and then type in your questions. So we'll probably hold questions till the end of Mark's presentation, or he might have a couple breaks in there. We'll see how it goes. But you should type in your questions at any point. You do not need to wait until we officially are asking questions. I'll be monitoring those, and I'll be the one that will actually ask the questions of Mark for him to address. So with that, I'm just showing you the NYMOA website in case people are curious about NYMOA, but then also to show you where you'll be able to find information about this event plus a lot of other ones that we do. So there's an events section of the website. Seems like my computer's a little slow here. Come on. And you'll see that this webinar is here. And then we've got another one coming up in March about deconstruction. It's related to waste site cleanup and brownfields because a lot of projects have buildings that need to be removed. So we're going to talk about trying to minimize waste from that and cost. That's coming up in March. So, but this event will be in the past. So the events are very forward looking. So you need to click this little arrow here. And then, like I said, I'm sorry, the computer's so slow. And here's all the webinars that have happened in the past. You'll find the most recent ones at the bottom. So, you can keep clicking to go backwards in time. So, but you'll be able to see, like, here's a webinar that we did back a while ago. And we can look there. I'll click on that. And you'll see here's a link to the PDF. And then if we recorded it, there'll be a link to the recording. So that's where you can find that. You can also find these events that NYMOA has done for waste site cleanup by going to the waste site cleanup program. And then I have a training section, and all the training that NYMOA has done year by year is listed. So you can go back and then you'll have PDFs of the presentations, plus if it was recorded, then there's recordings as well. So we've done a lot of things in the past. So, and this will show up. I'll make a 2025 section and we'll put this one up here as well. So So I just wanted to show you that about where things will get posted afterwards. Like I said, I will also send an email out to everybody that was on the webinar today to let you know and give you a direct link to the resources. So with that, I'm going to introduce Mark and read a little bit about him. So I'm going to make him the panelist and we'll show his screen. So Mark Domaracki is a professional geologist in the Division of Environmental Remediation at the New York State Department of Environmental Conservation. He manages projects primarily in the State Superfund program and the Brownfields Cleanup program. He was a geophysicist in the private sector responsible for Downhole Geophysics program at that firm prior to working for New York State DEC. His experience includes geophysical methods such as downhole geophysical logging, low frequency ground penetrating radar, resistivity, and seismic and electromagnetic surveys. He received his Master's of Science degree in Applied Geology from the University of Pennsylvania and his bachelor's degree in environmental science from Boston College. So with that, I'm going to mute myself and turn off my camera, and then yeah, everything will get bigger. So take it away, Mark.
All right, so can people see my screen? Hopefully
yes,
we're all...
Yep, all set.
Okay, great. All right, so thank you, Jennifer, for that. This is the Downhole Geophysical Investigations, Expectations and Applications to Contaminated Bedrock Groundwater Sites. Today is meant to be kind of an overview of what to expect from a geophysical investigation, a downhole geophysical investigation, and how to apply it to remedial sites. So before we kind of jump into that, I wanted to dedicate this to one of my mentors, Jutta Hager. She, this is appropriate because she worked out in the Boston area for over 30 years. She was actually one of the first women to receive a PhD in geology from Harvard University. So I wanted to kind of dedicate this presentation to her because she was one of my mentors. So the course outline, what we're going to talk about today, we're going to talk about the geophysical tools, what's out there, what's commonly used for remedial investigations. Then I'm going to talk about monitoring while construction, considerations when you're dealing with a remedial site, thinking about planning if you're going to do a geophysical investigation. Then we're going to talk a little bit about what should you expect from a downhole geophysical survey. What kind of deliverables are you expecting? And then I'm going to go into a case study. We'll talk about applications at a real remedial site. So the standard geophysical tooling suite is generally comprised of 5 tools: a caliper, an optical televiewer, an acoustic televiewer, a polyelectric and fluid probe, and a heat pulse flow meter. The reason I'm displaying them all here now is this is the standard suite, right? So if we have an investigation that we're looking into contaminated bedrock groundwater, we're probably going to want to use all of these tools. There are some limitations to all of these tools, but really it's using them all together, using multiple lines of evidence that we can get our best result from a geophysical survey. I guess before I jump into the tools, one of the things to talk about is when you're conducting these downhole surveys, you're going to be installing a borehole, and you'll have to think about planning and accessibility. So these tools are run on a winch system. Oftentimes it's a coaxial cable. a winch, which is you'll run these tools up and down the borehole. And so most of the time, you'll need to make sure that your site is truck accessible. So that's important to know if you're going to be planning this kind of survey. There are options to be a little more mobile and run these on like an all-terrain vehicle. But you should account if accessibility to boreholes is going to be an issue, just make sure that you're planning for that that extra level of difficulty. So first tool is a caliper. And oftentimes this is the first tool run down a borehole to confirm that your drilling went as expected and that you're not having a lot of collapses in the borehole. The way that it works is you'll send it down the hole, and it has these 3 arms that open up, and it uses voltage to measure the borehole diameter. And so as you run this tool from the bottom up towards the top of the borehole, it logs the borehole diameter, and the changes in diameter shown, I guess, in the red line on the picture on the screen, can correspond to locations of fractures. So let's say you drill, in this case, a 6-inch hole. You should be logging 6 inches or greater probably the whole time you're moving up. And then if you have an increase in diameter, most likely that is going to correspond with a fracture. For the most part, we use caliper logs in correlation with other geophysical logs that we'll see in the next slides. And then just one thing to note, I guess, is that if you drill a 6-inch hole, you probably shouldn't see the caliper showing inward readings, right? So there are a couple of checks that you can have to make sure that this is properly recording data. So the optical televiewer, this is a really an important tool. We're going to get a lot of information from this. So an optical televiewer is a high resolution image of the borehole. And essentially what you're doing is you are taking a 360-degree image and you're unwrapping it. So in the center of the slide here, you're going to see there's basically a fracture cross-cutting a 3-dimensional object, and kind of when you unwrap it, instead of getting a plane, you're getting like a cosine wave. This is, when you're looking at these images, sometimes you'll see these wavy features and you think, you might think, oh, this isn't like a planar feature, but it is in fact a planar feature. So the way that this tool works is that you're using a high resolution camera, and it's shooting down on a prism, which spreads the image across 360 degrees. So you're seeing the entire borehole wall for each kind of slice that it takes. This tool is excellent for imaging in air and clear water. It does not do very well with suspended sediment. So if you have boreholes with a lot of suspended sediment, you're just going to kind of log some brown imaging, and you're not going to get good data back. So that is a drawback to the optical televiewer. However, it is really good for analysis of lithology, mineralogy, any kind of borehole defects you may have. It will identify fractures. You'll be able to look at staining. Sometimes if you're at a contaminated site, you may actually be able to visually pick up on napple coming out of fractures. And that's invaluable, information. And some of the really important data that we get out of this is we're going to quantify fracture, stripe, dip angle, and dip azimuth, which we can use later on. Next tool is the acoustic televiewer, and this works a little bit differently. Inside in this, when you look at the image here, there's this white kind of cone at the bottom of tool, and it has a 360-degree spinning acoustic emitter. So it's emitting acoustic signals, and those are traveling through the out the white area there, through water, hits the borehole wall and travels back to the tool and is recorded. So one of the drawbacks of this tool is that it only works in the fluid-filled portion of the borehole. So it only works in water. The acoustic signal doesn't travel well enough in air, so we don't get those travel time returns. So that is a drawback. However, it does image really well through suspended sediment. So in the case of the optical televiewer, maybe you weren't able to get data in a really, a borehole with a lot of suspended sediment. You can run this tool and you'll be able to get very similar data. You'll be able to find fractures or, take a look at the borehole with this tool. So the acoustic televiewer records returning amplitude and travel time of those acoustic signals, and the output is a 360-degree false color image, and those are generally in the red, blue, yellow scale, and it gives us things like fracture, strike and dip angle, that we can use for our remedial sites. It also has, because the full waveform, the return signals also can give you some additional information on the relative density of the rock. It can give you a bonding log to make sure that your well is set. So there are other applications to the acoustic signals that return as well. Polyelectric fluid tools are, again, very important to remedial sites. Water temperature data. I kind of mentioned this with the caliper, that you're looking for multiple lines of evidence to make conclusions. Kind of the basis for a lot of the work that we'll do with geophysics is we're going to use our optical and our acoustic televiewers to find fractures, understand their orientations, but we're going to be also using some of this polyelectric, this gamma, this fluid data to tell us more about what's going on in the water, and are the fractures transmissive or not? Are they moving contamination or not? So the fluid data that we get back, temperature is going to be really important. Shifts in temperature often correspond to transmissivity within fractures. So that's going to be, it's an important tool. Also, fluid conductivity and resistivity are another way that changes in the properties within the borehole can help us identify transmissive and active fractures based upon the composition of the water. So this is, these are sensitive tools. The next thing is resistivity logs. They are, we're taking a look now at the rock. Resistivity is looking at the rock, and it's basically a Wenner array at 8, 16, 32, and 64 inches in separation. So we're looking at mineral composition, lithology, and pore space, a little bit less directly correlated to our remedial site, but understanding the geology at your site is going to be really important. And if you have a large vertical extent of contamination, it may be very important changes, to understand the changes in the rock. One thing that I will note about resistivity is that it is run with an isolation bridle, which means you have to be really careful about which data is valid, because there can be up to a 30-foot offset between, if you have a very shallow borehole, to having data which has not been interfered with by surface metals or something along those lines. So you may have to pay attention to that, and your contractor should they'll know about that. Also, it records spontaneous potential, and gamma readings. Gamma is naturally emitted by rocks, particularly clay and clay minerals emit a lot of gamma, so that will help us locate fractures. And then one of the important things about these tool stacks is that they can be run. If you have a PVC cased hole, it can look in the, I guess, in the overburden or the bedrock if it's PVC. Something like a resistivity log is going to have a drawback where you have to be a certain distance away from any steel casing. But something like gamma, you could collect across the overburden and the bedrock in a steel casing or not. I'm realizing I didn't kind of call it out earlier, but many of these tools are meant for bedrock investigation. That's important because the borehole needs to stay stable in order and open in order for us to run these tools. So this is application to bedrock for the most part. All right, finally, I'm going to talk about the heat pulse flow meter. This is a really important tool because it's going to tell us what fractures are transmissive, which is going to tell us about the fate and transport of our contamination on our site. And the way that it works is that there is a top and bottom thermistor, and it measures heat dissipation from a central heat grid. So there, and I'm not sure if you can see my cursor here, but there is, let's see, maybe you can see it now. This is a diverter. It basically prevents water from moving up and down the borehole unless it is, unless it travels through the tool. So there's the heat grid is located here, and this is the only opening for water to kind of travel through the borehole. They create some heat, and then they measure the dissipation of that heat. And if the heat dissipates up the borehole, it's captured, or down the borehole, it's captured. So this is run by, you'll collect all the other tools that we talked about earlier. So you'll collect the acoustic and the optical televiewer data, and you'll locate areas where you think there's fracturing, as well as the polyelectric and the caliper logs. And then you'll select areas of interest from the previous data to run heat pulse flow meter testing. And you'll first do that in an ambient setting. So you'll run this tool in the borehole, and you, without any pumping or any, just ambient. And you'll collect a series of data in the borehole. Then, after you've collected that data, then you will stress the borehole, which involves pumping out of the borehole up to 1 gallon per minute and bringing the borehole to equilibrium, and then measuring, and then running the test again and measuring the flow conditions using the heat pulse flow meter. Now, the minimum flow for quantitative analysis is 0.03 gallons per minute. However, you can open up these time windows a little bit more. So if, let's say you have a very, a borehole that's not showing very much flow, you might open up the window to see maybe there is flow, but below that 0.03 gallons per minute threshold, because 0.03 gallons per minute can be quite a transmissive fracture. So, there are options for low flow, but they're not quantitative. So this is potentially a very, very powerful tool for you to determine what is happening in the flow in bedrock. One thing that I want to stress is that I've seen a lot of contractors, when they do stress testing, just start pumping with, go into a borehole, just start pumping and running tests, right? To do a proper heat pulse flow meter, stress test, you need to record the pump rate to make sure that it's consistent during the entire test, and you need the borehole at equilibrium. That's really important because let's say you're pumping out at a half a gallon per minute and you are at equilibrium. If you have that type of situation, you know that the fractures within your borehole are supplying half a gallon per minute, and that those rates are the same. If you don't reach equilibrium, you don't really know where that water is coming from or if you have activated the fractures within your borehole. So by recording your flow rate, your head, those are really important aspects to doing a proper test. And if you are, if you're reviewing these work plans and these reports, you should make sure that this test is done properly and that you have this type of documentation. This is another tool which is not in the standard suite, but I think is really potentially helpful for people in the remedial field. A downhole camera is really nice. Sometimes you'll have kind of unexpected things pop up, like something may fall into your borehole, or you don't know what's going on. So a downhole camera has a couple advantages that are different than the optical televiewer, is that you can have a downhole view and a side view. It makes it really good for identifying mineralogy in rock. It also is good if you have some kind of void space or a breakout where your drillers are like, hey, something happened down here. This would be a really nice way to inspect something in a surprise condition underneath the in the ground. It's also really good for casing inspection. As I said before, it is really, if you have an obstruction that's blocking a borehole, this is a good way to figure out, is the rock collapsing, or is maybe something like the well cap fell in. This will give you some answers. All right, so I'm going to talk a little bit about planning and when you're planning an investigation. So if you know that you have a contaminated site and you're going to be investigating into bedrock, it's good to think ahead about what you're doing. And if you know you're going into bedrock and you're trying to figure out the extent of contamination, and it may make sense to do geophysics. I think there can be a lot of cost savings if going into investigation, you plan to do some geophysical investigation. If you are going this route, the first thing you're going to have to decide is drilling method, right? So if you go the geophysics route, you might be able to do a less expensive drilling method, which will allow you, cost savings right off the bat, and maybe pay for your geophysical work. So air rotary is an example of potentially a less expensive drilling method than coring, right? So if you're going into bedrock and you have to core everything, that is much slower, and it costs a little bit more. And you'll have some core, which will help you, right? But you're not going to get some of the information that the geophysics will get you, which will be, quantitative data on the fracture orientation. And then if you're doing geophysics, you can also do vertical boreholes, or you can do angled boreholes. So it kind of gives you, the option to get a lot of data on either a vertical or angled borehole. One of the things to consider, though, is if you are going to be doing geophysics, you need kind of the minimum of like the 4-inch diameter well. Most people don't drill 3-inch diameter wells, so generally it's that 4-inch diameter is the standard smaller size, or 6-inch. Those are common borehole diameters. So in order to get all the tools that I talked about earlier down the borehole, you do need like the 3 to 4 inch, the 4-inch diameter borehole to run these tools. As I referenced a little bit earlier, their imaging is not applicable for the overburden. So because we need this borehole to stay open, it's only applicable to the bedrock. We might be able to get some data in the overburden, but this is for bedrock contamination. And then in the next slides, I'm going to talk about cross-contamination considerations, right? Because if we're working in bedrock, we don't want to inadvertently kind of open some pathways for migration. So continuing on this planning theme, we need, when we're planning an investigation and we're planning to do some geophysics, we need to think about the next steps. So understanding your order of operations, once you drill a hole, the borehole needs to be open to run the geophysics. So you'll set the casing in the overburden, and then your geophysics will be run in the rock portion of that borehole. However, kind of the next steps are important too, because if we know that we're working on a contaminated site, we should be thinking, what are the next things that we need to do? Because this is not the only, doing the geophysics is not the end game necessarily. We want to, monitor groundwater. We want to know, we want to get information from this beyond just the geophysics, right? So if you're going to do a packer test, do your geophysics and then right behind it, do a packer test. After you've done that packer testing, now is the time for well finishing. So you can either use your geophysics to help you set a single screen, or there are some other opportunities, right? So if you do a large enough well, you could do a nested well. There is something called continuous multi-channel tubing, CMT wells, which have you can have multiple intervals. You'll have multiple intervals within one borehole, and kind of everything else will be sealed off. There are flute wells, which is the same idea, slightly different technology, where you can have multiple monitoring intervals within the same well, where everything else is sealed off. And then double cased wells. It's just another consideration for cross-contamination in terms of the structure of the well once you're done doing the geophysics. And so today I'm going to talk a little bit about a case study which involves geophysics, and it also involves implementing some of this flute technology. Flute has a bunch of different products. But one that I want to talk about here is the blank liner. So if we're doing a geophysical investigation, or we're on a remedial site where we're investigating potentially really high levels of contamination in bedrock, it may make sense to do a blank liner. And what this allows is you can drill a hole, and then you basically install this liner, which prevents any vertical migration of contamination, or prevents the borehole from becoming a conduit for transport of contaminated material, right? Because that's the last thing we want to do. So this is a technology that will help you in the planning phase make sure that you're not allowing for that pathway to exist by installing a blank liner, and you're not creating a vertical pathway for contamination. They also have these knuckle liners and tack liners, which go in, they would go on the outside of that blank liner, and they allow you to kind of collect additional information while that liner is set. So you can find out if your fractures have NAPL in them. They can tell you approximately how much contamination that liner has come in contact with. There's some information about transmissivity that they can get as they remove those liners. And they also do a multi-level monitoring. So you can install monitoring points at various elevations in that borehole, which I'll talk about when I get to my case study. So I just wanted to bring this up because the geophysics is really important. It gets us a ton of information, but we also have to think about the application to the remedial site. All right, so you're planning on doing a bedrock investigation. You know you have contamination. What should you expect from a geophysical contractor? So the first thing that should be expected is geophysical logs, so image logs. And we're gonna take a look at those. Some of the things that are important are also structure tables. You're gonna wanna know the strike, the dip azimuth of these features. Because in bedrock, discrete fracture fate and transport, occurs, and so we want that data. There are rows and stereo net diagrams. They tell us kind of regionally what maybe, or at the local level, what is going on in the geology on our site. Deviation plots will tell us a lot about the drilling of our borehole and if it is where we think it is. And finally, the heat pulse flow meter graphs, they'll tell us a little bit about the hydrology within our borehole. And then reports, we should expect some reports for our deliverables. So geophysical logs, what do they look like? What should be there? Every contractor's logs look a little bit different. However, this is an example of a good log, right? So on the right side here, it looks like we have potentially some kind of sandstone. You can see that there are, on the far right here, this is an optical televiewer log. We see some potential fractures, right? It looks like they're, potentially fractures there. To the left of that log, there's this false color image that I talked about earlier from the acoustic televiewer, the yellow and the blue. The yellow is hard, competent stuff, and the blue is a lower amplitude response. And so now you can see, really stark contrast between the hard rock and the areas that are potentially fractured, right? We're seeing this sine wave up here, and they're really well correlated, the acoustic and the optical televiewer logs. On the far left here, we're seeing the geophysicist's interpretation of the features. So he or she has traced out these features, and now, so you can see, what they've selected as the feature. So you should expect the end product of your investigation to include these geophysical logs. You should have fractures traced and categorized by your consultant, and you should understand how they're orienting the data, because that's going to be really important. One of the things that I see a lot of is contractors just spitting out magnetic north. In the NMOA region, right, that ranges from Maine to New Jersey, right, that could be 15 to 18 degrees of difference of magnetic declination. So that's the difference between magnetic north and true north. So 15 to 18 degrees is really big, right? So making sure that your contractors are putting your orientation to true north is important, and one thing that you should be potentially checking out to make sure that they're doing it, so you know how to use the information that they're providing you. And then logs should be correctly scaled and labeled. Pretty soon I'm going to go into some examples of bad data or bad scaling, and you'll see. All right, so here is some good optical and acoustic data. Up top here, you'll see that, again, there are some features that are visible in the acoustic log that are a little bit harder to see in the optical log, but having both really helps get to get a good picture and to select features. And then again, we talked about the one below. What does bad data look like? Well, this is some really bad data. People, this is data that has been submitted to the DEC. You cannot make any interpretations on this data. So you'll see these two giant stripes. That means that when they ran this data, or when they ran the tools on the survey, they didn't centralize the acoustic televiewer. So because it's not centered, it's I guess lying against one of the borehole walls on one side, and it's kind of blown out the travel time log so much that we can't see any features. In the middle is an optical televiewer log where mud or something along that lines is stuck to the screen, so you're not getting a clear picture. Instead of submitting data that looks like this, they need to brush the screen off and try again. Again, here on the right-hand side, the data is so interfered with that you can't make any determinations on the features. So watch out for poor centralization of tools, because if they do it improperly, you're not going to get any data. So this is what bad data looks like, and it needs to be run again. It's not useful. Another thing to look for is inconsistent interpretation. In these two examples, features are not consistently interpreted, right? So when you get data back from a geophysical contractor, go in, take a look. Does it look like they've been consistent in their interpretation? Because it potentially is going to be really important for you later on when you go to use this data and incorporate it into the other data that you have on your remedial site. Again, here's another example of inconsistent interpretation. Really poor data quality on the left-hand side for this acoustic televiewer. And then on the optical televiewer, you're looking at it and you're like, I don't see most of the things that are picked here. So if you can't tell why they picked something, it's probably best to ask. And in this case, the data interpretation is poor and the data quality that they collected is so poor, they may have to go out and do this again. All right, orientation errors. If you see logs like this, you should kind of alert yourself that something may be going wrong. You saw the examples of bad data from the previous slides. Here is another layer that can be put onto it. Not all the time are consultants going to show you on this left-hand side, this blue, it's called an azimuth log, and that is what is used to orient your data. That azimuth log is shifting wildly, right? That might be due to some type of interference. It might be because the tool is not centered. But if that log is shifting like that, that is how we are going to get the data for our fractures. And that value should, if the data is collected correctly, that azimuth line should be straight. So if you see wild fluctuations in your images, you may have to ask for that azimuth log. And if you see something like this, where the azimuth log is wild and it's not a straight line, it's time to start asking questions. Here, they've not only have they collected some really bad data, but they've done interpretation in the areas where they've collected poor data, right? Which is going to be very misleading. If the azimuth information is off, in this case, it's off almost 180 degrees, they've interpreted fractures that are not properly oriented. So if they tell you that this fracture is dipping in a certain direction, they don't know that because the tool is not properly oriented. So that's something to keep an eye out for. If you see really poor quality data, you're going to have to question if the underlying orientation data is correct. I talked a little bit about the declination. Make sure you understand if the declination correction has been incorporated into your data, because if you go to use quantitative data from fractures without understanding if it's referenced to true north or magnetic north, that's going to make a really big difference on a site. And again, if the images look distorted, ask questions, because there may be something wrong. And I see it, unfortunately, done incorrectly quite a bit. Setting reasonable ranges. They're going to provide you some of these logs, and you got to make sure that they're providing reasonable data. These are two logs that were from the same site. One of them has a negative fluid conductivity. Fluid conductivity should be a positive number, so there's no reason why fluid conductivity would be negative. So they didn't set this range. I don't know how that happened. And the borehole next to it has a wildly different range. So unless there's some reason to expect that between two boreholes, the fluid conductivities would be wildly different, you should be questioning and you should be asking them to make modifications to this. The same thing goes for the temperature. They should be making sure that their ranges are appropriate, because that will also help you determine if look at the data and determine if anything is going on. Ooh. So, again, setting reasonable ranges, the same thing as the last time. The ranges for one particular site should be in the same ballpark. In this example, they are all over the place. Something is wrong. They should be explaining themselves if the ranges are wildly different. So that's one thing to just keep an eye out for. All right, structure tables. So this is what's going to come back from the optical and the acoustic fracture analysis. You should, at a minimum, be given the depth of the fracture, the true dip azimuth, and the true dip angle. That's really important information, as well as some type of description code. So is this the the big fracture that I think it is? Can I take a look just at this fracture and determine what direction groundwater may be heading in? If you're in a bedrock situation, right? So Rosen stereo net diagrams will give you an idea of what orientations are you generally looking at in your borehole. Is your fracture orientation for your site relatively consistent? Are most of your fractures potentially in a bedding plane or something along those lines? That will really help you get a better understanding of bedrock groundwater flow at your site. Deviation plots, these things can be important. They're essential for angled holes, but you install a well, you kind of think generally, oh, the bottom of the well is right below my feet. But in reality, these things kind of walk away. They deviate from where they started. So in this case, this was a 250-foot well. It moved about 8 feet to the east, so it's just a good thing to know. If you're doing an angled hole, you want to know where you ended up. So heat pulse flow meter. We talked about it a little bit earlier on, but there's ambient testing where you're not doing any pumping. And this can help identify some natural flow conditions in the borehole. And the stress testing, which is done as well, you need to prepare for. So if you are going to do a heat pulse flow meter test, you should prepare for IDW of the pumping water. That means you probably want a couple 55-gallon drums on site to collect that water to, so you can, so you're not discharging to the surface if it's contaminated. So in general, sometimes these get pumped at about a half gallon per minute. So if you're doing an hour test, you should, prepare for about one 55-gallon drum per borehole, depending on what you're doing. But that might be a good rule of thumb unless you have a reason for more or less. I talked a little bit about recording those pumping rates as well. And I also talked about, the importance for groundwater to be at equilibrium, right? So we're activating fractures. We know what we're pulling out is also what the fractures are bringing in and resupplying, and that's why we're at equilibrium. So under that stress test, we know we're at equilibrium, and we know we've activated fractures, and so we should be able to record that. And on the right hand side of the slide here, there is so in the blue here are numbers. On the left hand in the blue is the ambient. On the right is the stressed. You can see that the changes in these numbers. So these yellow areas here, this black line is a caliper log. We're looking at how much water this particular fracture is producing, right? So we see that under stress conditions, maybe there's some minor inflow from the bottom of the borehole, but once we get above this fracture, we're producing a bunch of water, 0.19 gallons per minute. And then we're getting to 0.25, and then it kind of stays the same, right? And then it, so we know that something's going on here at this location, at this location in particular. In this location, we know that there's a change in the flow that or we know that they're transmissive and they're providing flow into the borehole. And then here we see that there's a large fluid conductivity spike. That tells us that the bottom of the borehole is different than the top, and that the fluid conductivity is very different. So that's kind of like another, when you see shifts in these fluid logs and you see fluids coming in and out of the borehole, this is a key that, there's some transmissivity and there's the ability for the rock to transmit contaminated groundwater. Again, I talked about this a little bit earlier, but recording your stress testing is important. Understanding that you want to be at equilibrium when you collect this data. Reporting, so what are you looking for from the reporting? You should look for your geophysical contractor to provide you with those image logs and the supplemental stereo deviation logs. And then it's important to get some kind of report analysis back. Maybe they're providing some basic geological background. They should be talking about their interpretations and conclusions. You should be looking for it to be supported by multiple lines of evidence. So if you have a fracture, you have a fluid shift, you have a caliper, shift indicating that it's a fracture. Those are multiple lines of evidence to draw a conclusion from. And then the fracture orientation data, that's going to be important for the applications to the next step, which is you as a project manager. You want to take a look at that fracture orientation data because it's important, maybe we'll want to take a look at discrete fracture sampling. And I'll talk about that in my case study. Is it's important to take a look at particular fractures because not every fracture is going to necessarily be containing contamination. So if we can reduce the amount of area that we need to remediate or investigate, that's going to be beneficial. So after we get this geophysical reporting back, we're going to be able to update our conceptual site model. So hopefully we'll be able to identify migration pathways. We'll use an updated conceptual site model potentially for proper placement of new monitoring wells, whether that be we're going to look for horizontal delineation or maybe we need additional vertical delineation. By looking at the fracture orientation data, we'll be able to place properly monitoring wells to ensure that we're monitoring fractures which are significant. All right, getting to the case study. So application of geophysics to a remedial site. All right, so just kind of real quick in this hypothetical real site, we have a site that has, done machining of metals. It used a lot of spent solvents, including a lot of TCE, where it was historically released to the subsurface through a basement sump. So, it's important to know, as a lot of you know, right, know your contaminants, right? TCE is a potential DNAPL. So we should, just knowing our site contaminants, we may be concerned that if spent solvents were discharged to the sump, we may have a DNAPL issue. So in this case, we had a couple overburden and bedrock wells. We did some pump tests on them. At low flow sampling, we got pretty high concentrations, but at each successive iteration of our pump tests, we got higher and higher concentrations. That was indicative that we had DNAPL present. So it's time to look into the bedrock at this site. One of the things that you want to do before kind of conducting an investigation is check out your regional geology. So in this case, we were in the Manhattan Prong. There's a lot of faulting associated with tectonic thrusting in this area, a lot of deformation, localized weathering. So for this site in particular, we knew that we were going to be in the Manhattan Formation or the Fordham Gneiss, probably the Fordham Gneiss, but we'll see, as we kind of get a little further along, we'll see where we actually are. Again, we're probably in the Fordham Gneiss in this case, a lot of tectonic movement, metamorphosed rocks here. So lo and behold, we go in, we start installing bedrock wells. In this case, this was a cored well, but that was prior to our geophysical investigation. But just for another nice picture here. So we're in the Fordham Gneiss, right? So our geophysical investigation, we come in, we take a look. Wow, all right. Geophysical investigation helps us pay off, right? It backs up our regional geology. We know we're in the Fordham Gneiss. We have some nice, images of what the rock looks like, and we can confirm, right, that it's a highly metamorphosed rock, and it's very competent. So, what about the groundwater flow? We know something about the overburden here, so we know that it flows to the southeast. But does the bedrock flow direction always follow the overburden? No, right? So we have to start thinking, in a different way for the overburden issue versus the bedrock issue. Through our pump tests, we found, and some overburden monitoring wells, and our bedrock monitoring wells, we found that there was a downward vertical hydraulic gradient. So not only do we have DNAPL, but we're expecting the groundwater flow direction to be into the bedrock. So another reason we need to start investigating into the bedrock. And then what about flow directions in discrete bedrock fractures? So in the overburden, things are very, potentially, right? Potentially could be homogeneous and more simple. Whereas in the bedrock, we start thinking in discrete fracture orientations and networks of fractures and primary directions of dip or flow. So things get a little more complicated as we get into bedrock. And we're thinking, so we know our contaminant of concern is a TCE of VOC that's going to act like a DNAPL. How will DNAPL migrate? And how can we use geophysics to help us figure out what's going on in the bedrock? All right, so we're planning a survey, or we're planning to investigate. What do we need to consider for our monitoring wells? So we already talked that we're concerned about DNAPL, and we want to do a geophysical investigation, but we also don't want to create this vertical pathway for DNAPL to start shallower and get deep. right? So that's a real concern here with DNAPL. So one of the things that we did was we used a blank flute liner and fact liner to prevent DNAPL cross-contamination. So this is a picture of the guys there out in the field from Flute installing the liner. And in our case, we used a fact liner as well. And I think it's the next slide will show you what a fact liner looks like. But essentially by putting the fact liner in and then putting the blank flute liner in, we were able to install the well, do geophysics right after the drilling, and then have these guys come in right behind them. So the borehole was only open a couple of days before it essentially got shut off from any, cross-contamination concerns. So this, we drilled the hole, we put this liner in, and now we're going to have a little bit of time to evaluate the results that we get to determine what the next best steps are without having cross-contamination. So I'm going to play this video. Hopefully it plays. So this is the NAPL fact liner has been taken out of the borehole, and we decided to do 2-foot sections. So this was up against the borehole wall, and then they took it out, and then they're going to cut it into different sections. And they take this activated carbon strip here, and they're going to throw it in, and they're going to sample it. So this allows us to not only do we have the, play that again. Not only do we have the geophysical information to tell us where the fractures are, but this is going to give us information about discrete fractures and if there's NAPL or if there's contamination emanating from those fractures. So really important information if we're going to figure out the nature and extent of the contamination, and if we're going to optimize our remedy, right? It's going to be really important to know where we need to treat in the bedrock. All right, so we did some of that NAPL liner, that fact liner, and we found that there was contamination in some areas across wide swaths of the borehole. In some cases, it was only in select portions of the borehole. So for some of the boreholes, we did a flute system where we set up 3 different monitoring well intervals within one borehole. So we're able to monitor 3 vertical intervals within one borehole. So obviously, you'll have to install this system, which is a cost, but you'll not have to drill 2 other wells, which is helpful. So that's a potential cost savings, where you're investigating in the bedrock, you're able to monitor multiple intervals, but you're only installing 1 well. So potentially helpful. One of the drawbacks here is that, there's additional cost to installing a multi-level well, and that these these monitoring intervals need to be at least 5 feet apart. But you can have anywhere between 3 and 16 intervals. So if you have a really deep hole, hypothetically, you could monitor multiple intervals with only having to drill 1 borehole. So that's a potential advantage. So let's take a look at this this case study, right? So this is one of the monitoring wells, one of the boreholes, and I'm going to kind of bring your eye here to this dark blue here at 24. So again, we're in the NYS. We see, oh man, this looks like a big fracture, and then we look at some of the flow information that we get, and you know what? 24, we're getting most of our flow coming from this area, and at 27 we're getting flow, and these are big fractures, right? And you're like, well, this might be, where all the contamination is coming from. And then there's this little thing down here at the bottom. It's also characterized as a larger size fracture here in red. Okay, well, there's one at the bottom, but we might look at, if you were to collect just a groundwater sample from this, you might think, oh, the top where it's really transmissive, that's where we're getting all our contamination. Well, let's see. So again, here we are, we're thinking this fracture here at 24, we see some flicking slides, we see some clay forming here, indicative of it being transmissive. We see nice fractures here at 27. We have their orientation, they're dipping here. The dip azimuth is 223 degrees, so that's what, southwest. You know, the dip angle is in the 40s. So we might think that's the direction to go. But hold on. We have our bedrock geophysics, but let's incorporate some of that flute information that we took. So when we look at our site COCs, we have all these different VOCs, and we did some fact finders here. So at first we thought maybe 24, 27 was our area of interest, really transmissive. You know, if we took a groundwater sample here, we might, you know, jump to the idea that, you know, our most transmissive fractures are carrying the contamination. However, when we look at these flute liners, right, our TCE is really taking off at this, you know, 47, 48 interval across all these different site COCs. So although, you know, this may have looked initially like it is the fracture that's creating a lot of the contamination, by incorporating some of this flute technology, we're able to isolate our NAPL from coming from this 46, 47, this smaller diameter fracture near the bottom of the borehole. So what does that look like in a composite log? Well, here we go. We're overlaying now all of our information. We're taking a look at our geophysical, our optical televiewer, our acoustic televiewer. We're looking at our caliper. We're looking at our interpretation. We're looking at our heat pulse flow meter data. We're looking at now the flute data and incorporating it, right? So we had some, you know, so we're, instead of looking here where we had, you know, some large fractures and some transmissivity in our heat pulse flow meter, and our flute transmissivity test showed that this was wildly transmissive, but we've also found that we're not getting much contamination in this area. However, when we look further down the borehole at the smaller fracture, we did find flow in the heat pulse flow meter. And lo and behold, bam, here we have our NAPL coming out, and we've detected it in our flute liner. So this is going to be, you know, really helpful for figuring out how to treat and how to install a proper monitoring well network to look at discrete fracture flow from this particular fracture. Oh no, what happened? All right, there we go. All right, so now, let's see, things are, all right, I can see again. Okay, so that fracture at 46, 47 feet, you know, now let's try to make sense of that. Why is that fracture?
Mark, we're still seeing your original, the first slide plus the slides down the side. So
All
it's
right.
not in slideshow, and we're not where you were. I don't know what happened.
Yeah, I had it flickered there and I lost it. Let me, all right, do you have anything now?
No, I'm not seeing anything now.
All right, let's see here. Just 1 second, I'm trying to.
Okay. Yeah, you must have inadvertent. Oh, okay, there's the slide. We just need it now put in slideshow mode.
There you go. You good?
Yeah.
All right, so
Okay.
So, all right, so we had this surprising result, right? We have fractured deeper, which is heavily contaminated. However, above it is highly transmissive and not contaminated, right? So how does that make sense? So let's go back to some of our site data. So our VOCs were disposed of in a sump in the yellow outlined area. So it was discharged to essentially the sump, and then out of the sump it came, and then this green line represents that fractures, where that fracture would project to hit the bedrock surface. So as my previous slide showed, but you can't see now, the direction of groundwater flow is to the south and east. And so if the the location of the sump makes sense, so it was a DNAPL in the sump, it traveled in the overburdened groundwater, hit the top of the bedrock, potentially traveled along the top of the bedrock, and then into potentially this green fracture, and then traveled within the fracture, then down to depth. So this is helping us update our conceptual site model, right? So we know approximately where the contamination was released. We're starting to see some fate in transport. So let's look at some other monitoring wells in the area and see if we can make more sense. So this is another monitoring well, and again, we did some flute testing here, and it's a little bit deeper. And now we don't have that smoking gun, that discrete fracture, right? We have, if you look down here at the bottom, we have contamination, but we have it kind of across multiple fractures, and they're in similar orientations. So this is the situation here where we set up multiple monitoring intervals. So we can monitor, we drilled one well, but we're monitoring 3 sets of fractures. And primarily, all those fractures were in the same type of orientation. They were in the 300 to 330 orientation. So they're pointing west, northwest. So that's a slightly different orientation than the one we had before. So now I'm starting to look at not just, all right, I know where my source is. I know what the, potentially what the primary driver, where the contamination starts and where it's, first coming out, but where is it going down the line? All right, so now I'm starting to bring in more monitoring wells, and I'm bringing in that geophysics. Primarily, we have all of our larger size fractures, our rank 2 and our rank 3, in this western direction, right? So we do have a fracture which is transmissive, bringing NAPL level contamination. However, at some point, that fracture is into a network of fractures, which is primarily in the west, dips to the west. So we're not seeing overburdened bedrock groundwater migrating in the same direction that we see the overburden. And we know this because we have analytical data, and we also have this fracture orientation data, which meets, with the analytical data that we're getting from these monitoring wells. So what does that look like? Well, now we've kind of isolated our problem a little bit. So we've installed these aren't the only monitoring wells on the site, but they help us drive home the point here that we were able to update our site conceptual model because we mapped these fractures. We know that there are discrete fractures where contamination is migrating, and we're able to kind of close off some other avenues through analytical results and through fracture orientation to isolate or to identify what the bounds of our issue are and have a really robust conceptual site model. All right, so getting here to the conclusions, what are the applications of geophysical surveys? It's going to update your geological understanding from the regional geology to site-specific local geology properties. Really important. We're going to potentially identify discrete transmissive fractures with orientation data. That is going to help us implement optimize a remedy or optimize any additional investigation we need to do. It's also going to help us create an acceptable monitoring well network. In this case, we talked about Fordham gneiss and folding structures, but if we're going to do a remedy, this is going to help us optimize our remedy. We're not going to be, potentially injecting in this highly transmissive area with no contamination. We're going to isolate it to the contaminated fractures. And we're going to do that because we have an updated conceptual site model. So those are some big, applications of a geophysical survey that potentially can save you money on a remedial site. So in summary, we talked about the different geophysical tools. We talked about monitoring well considerations, what you need to do when you plan for an investigation of this type. We talked about the deliverables you should expect, good data, bad data, kind of what it looks like. And then we talked about finally an application to a remedial site and how we use some of this information. All right, and that is all I have. Any questions?
Okay, great. Well, thank you, Mark. That's a lot of technical information that I think, yeah, we don't have any questions that have come in that I can see. So people, please type them in, but I will ask some that I have because I always have questions. And keep in mind, I have not worked, done site work in quite a while. But I'm wondering about those liner systems. So you're going to do your geophysical work before you put the liner in, or somehow or another it can work through the liner?
Right, so it's important. So the liner gives you flexibility, right? So you don't want to create this open conduit. And when you're drilling bedrock wells, you need the open borehole to do your geophysical imaging. So you can install the well and then do your geophysics, seal it up while you determine what you need to do in terms of, do you need to screen particular areas? Do you, you can figure out your monitoring well construction in that time and have time for the geophysics to get turned around and, make your plans. And then you're using that liner to make sure that you're not allowing cross-contamination while you do those other aspects of the project work.
Right. And then, okay, so yeah, so it's a method of sealing, temporarily sealing, and then you remove it. And if it had the activated carbon system, then you can do analytical testing on it as well, it looked like, correct?
Yes, correct. Yes, you can.
And then when you remove it, now you've got the cross-contamination issue, but because you've analyzed everything and figured it out, you're going to isolate certain sections so they can't cross-contaminate,
so you can leave these liners in for long periods of time, but you should, if you have cross-contamination concerns, right, at some point you should finish, you shouldn't leave an open borehole. You shouldn't leave it open borehole if you have cross-contamination considerations. So there should be a finishing, whether that's, decommissioning it or installing a well screen and grouting the rest up so you're not allowing it. So there are a whole bunch of ways that you can finish the monitoring well, but all the work that you do prior to that, potentially geophysics or packer testing or, whatever route you go, that all needs to be done on open borehole.
Okay. So we've got someone questioning about just the presentation slides and the recording, and yes, they will be posted. Just a reminder about that. But I have another question. If you went back to some of your bad data slides, maybe I didn't quite get everything. I don't know if we can go back. Yeah, they're kind of back farther. The case study was super interesting. Yeah, when you were talking about the azimuth and the one where it was wavy, where was that wavy? The problem one?
Yeah, so
there. Yeah, where is the azimuth that you're talking about not being correct?
Yeah, so
Which one is
on
that?
the left-hand side, that blue line there.
Oh.
So you see this blue
What's
line
the
here?
red line then? What's the red
So
line?
the red line is the tilt of the borehole. The red line is the tilt. So
Oh,
the
okay.
tilt and the azimuth are critical information for determining the orientation of those features. So those
Got
go
it.
all into the exporting the calculation of the orientation, right? So if you have improper orientation in those sublogs, then the exported information will be incorrect.
Right. Yeah, because that blue line, I was like, is that the blue line showing where the fractures are? I was what that was. So, okay. So the blue line in theory should be straight and okay. Got it. Okay.
Yeah, that's that's kind of like a level of detail that it's like I've seen so many of these. I don't think everyone would pick up on that necessarily, but it is something that, as working as a regulator, right? I now see a lot of the product that comes into the DEC here in New York State, and these are some of like the major issues that I'm seeing over and over, is that people aren't properly processing it, and this can potentially be dangerous if you are doing something actionable with this data. This is kind of a common mistake that I see.
All right. Well, those are some things that just on a basic level, not again working on sites that I wasn't clear on. Is there anything else anybody has? All right. Well, that was super informative, and I think everybody was looking forward to being able to study the slides and listen to the recording again. So, yeah, I don't think there's any harm in ending 8 minutes early. So, thank you so much, Mark. And I will be emailing everybody that was on when we get the recording and the slides posted. So, thank you again, Mark. Take care. Hope everybody enjoys the rest of your day. Bye-bye.